So in this video, I actually want to calculate the dot product. And of course, the actual calculation is not hard at all. You begin by finding the product of the x's and the product of the y's, and then you simply add them. So 3 times 1 is 3, 6 times 3 is 18. You add them together, and it is 21. And just, to kind of think about why these numbers are what they are and how they relate to what we talked about. If you have a vector here that's going over 3 and up 6, so it's very, it's moving up and to the right, that's the direction, and then it's acted upon by another vector going in the same direction. It makes sense. This would be a pretty big vector, okay? Then we do the same here. So negative 8 and 36 makes 24. And in this case, I think sometimes you'd say, well, why is this number so big? Because this went back and up. Well, this one is acting upon it in the opposite direction for x, but you can see it's acting on it in the same direction in y, and very strongly. So that's why it's as big as it is. Negative 1 times 3 is negative 3, plus negative 6, plus 24. So we have 15. Now, finally, I wanted to say, well, what happens when you dot something with itself? And I think the easiest way is to just maybe draw a quick, or make a quick little sample vector. So you'd have a squared plus b squared. When you dot a vector with itself, that should look familiar. You get the magnitude squared. And again, this goes back to what a dot product is. If you have a vector and then it's being acted upon by the same vector, it's pushing in exactly the same direction. And that's why it makes such a powerful effect. So using the other formula for dot product, this one, I'm going to use that quickly to find the angle. And I'm going to do a little algebra up front. In order to find an angle, if I take the dot product and divide it by magnitude A and magnitude B, and of course, then to find theta, you could use the inverse cosine function, like this, and that would give you theta. So dotting these two, I did that on the previous slide. 3 times 1 plus 6 times 3 is 21. Magnitude of the first vector is 9 plus 36, so it's the square root of 45. The magnitude of the second vector will be 1 squared plus 3 squared, and the square root of that, so like this. So then if you do the inverse cosine of that, that will be theta, and I'll let you type that into your calculator. Okay. This next example we'd already dotted. The dot product was 24. So on top, using the magnitude formula, we've got negative 2 squared plus 4 squared, so square root of 20. And then we've got 6 squared plus 9 squared, so 36 plus 81, the square root of 117. So this is inverse cosine of that. All right, finally, how would you know if two vectors are perpendicular to one another? Well, perpendicular, of course, means 90 degrees. The cosine of 90 degrees, or pi over 2, is 0. So thinking about this formula, obviously the magnitude of vectors isn't going to be 0. So if this is going to be 0, you need the dot product to be 0 in order to make the two sides equal, because this part of the formula won't be 0. So two things are orthogonal if they dot to be 0. And I want to just think about this geometrically for a second. If I have a vector and it is acted upon by a vector that is orthogonal to it, notice that it's not pushing my original vector any further in its direction, right? It's not pushing it this way or this way. It's not pushing it at all along its own direction. It's also not pushing it in the reverse direction. So it's pushing it in a way that doesn't affect it at all, and that's why its effect, its scalar, will be 0.